Welcome to the CompTIA A+ Prepcast presented by baremetalcyber.com. Solid-state drive interfaces play a critical role in determining both performance and compatibility when installing or upgrading storage in a computer system. The interface used by a solid-state drive not only affects how fast data can be transferred, but also dictates the physical form factor and how the drive connects to the motherboard. In the A+ exam, technicians are expected to recognize and compare different SSD interface types. These include SATA, PCIe, M.2, and mSATA. Each one has its own advantages, limitations, and usage scenarios in desktop, laptop, and enterprise systems. SATA solid-state drives use the same interface as traditional SATA hard disk drives. This makes them an excellent upgrade choice for systems that originally used mechanical storage. SATA SSDs connect using a 7-pin data connector and a 15-pin power connector, typically through a 2.5-inch drive bay. While they deliver significant performance improvements over spinning drives, SATA SSDs are limited by the 6 gigabit per second ceiling of the interface itself. This means that the full potential of the solid-state memory is not reached, but the drive still feels much faster in everyday use. When comparing 2.5-inch SATA solid-state drives with traditional hard drives of the same size, it is clear that the form factor and connectors are physically identical. Both use the same mounting hardware and cable connections, allowing users to remove a hard drive and drop in a solid-state drive with no additional parts required. However, the internal technology is vastly different. SSDs contain no moving parts, which results in faster boot times, quicker application launches, and improved reliability. For systems still using mechanical drives, replacing them with SATA SSDs is often the simplest and most cost-effective upgrade. PCIe solid-state drives provide a dramatic improvement in speed over SATA models. These drives connect directly to the central processing unit through the PCI Express bus, bypassing the slower storage controller pathways. PCIe SSDs are available as plug-in expansion cards or in smaller formats such as M.2 modules. By using multiple data lanes, PCIe drives achieve higher bandwidth and lower latency. This makes them ideal for high-performance workloads such as video editing, software development, and virtualization. They are a preferred choice for users who need maximum throughput and system responsiveness. The number of PCIe lanes allocated to a storage device directly affects how much data it can handle at once. A PCI East X4 drive, which uses 4 data lanes, can transfer more data per second than a PCIe X2 model. Some M.2 slots are electrically limited to only 2 lanes, which means they cannot take full advantage of faster SSDs. In contrast, desktop expansion cards installed in a full X16 slot can potentially access all 16 lanes, depending on the motherboard and chipset. For exam purposes, understanding the relationship between lane count and performance is essential. M.2 solid-state drives are among the most compact and versatile options available. These drives are printed circuit boards that plug directly into a socket on the motherboard, eliminating the need for power and data cables. M.2 SSDs can use either the SATA protocol or the NVMe protocol over PCIe. This means that 2 M.2 drives that look similar may offer completely different performance levels depending on the underlying technology. Technicians must confirm which protocols a given M.2 slot supports before installing a drive, as mismatches can result in non-functional devices. M.2 drives use keying to indicate compatibility with the host slot. A B key indicates compatibility with SATA or PCIe X2 interfaces. An M key is generally associated with NVMe over PCIe X4. Some drives feature both B and M notches, allowing them to physically fit in either slot type. However, the electrical signaling still needs to match the motherboard's supported interface. The keying system is a visual and mechanical way to prevent incorrect installation. On the A+ exam, identifying drive key types and knowing their compatibility is a tested concept. mSATA is a legacy compact storage interface that was popular before M.2 became the standard. mSATA drives are small rectangular modules that use the SATA signaling standard but in a compact form. These drives are not electrically or mechanically compatible with M.2 slots. mSATA was commonly used in ultrabooks and some embedded systems. While less common in modern devices, technicians may still encounter mSATA in older laptops that require replacements or upgrades. It is important to distinguish mSATA from both standard SATA and M.2 formats. The U.2 interface is another option used primarily in enterprise environments. U.2 drives look similar to 2.5-inch drives, but use a different connector and protocol. These drives offer NVMe performance by connecting to the PCIe bus through a U.2 cable. U.2 supports hot swapping and high IOPS operation, making it ideal for data centers and high-throughput systems. While U.2 is not commonly found in consumer hardware, it is included on the A+ exam due to its relevance in server infrastructure and advanced storage arrays. When comparing the SATA and NVMe protocols, the most important distinction lies in their design. SATA was originally developed for mechanical hard drives and adapted later for use with solid-state storage. Because of this, SATA imposes limitations on how quickly data can be read and written. In contrast, NVMe, short for Non-Volatile Memory Express, was designed from the ground up for use with flash storage. NVMe leverages the full bandwidth of the PCI Express bus and supports a much deeper command queue. This leads to lower latency and greater parallelism, which translates to significantly faster performance in real-world use. Technicians often need to identify an SSD interface type by visual inspection alone. SATA drives typically have two separate connectors, one for data and one for power, arranged as a pair of thin rectangular tabs. M.2 drives are smaller and lie flat against the motherboard with a screw to hold them in place. They have gold-plated edge connectors with notches for keying. PCIe drives that plug into expansion slots resemble graphics or sound cards, with a full-length edge connector that fits into standard motherboard slots. Recognizing these physical differences is necessary for installation and exam scenarios. Boot support is a consideration when installing solid-state drives with newer interfaces. Most modern motherboards support booting from NVMe drives, but some older systems may require a firmware update or a dedicated add-on card. Basic input-output systems, or BIOS, often lack native support for PCI Express storage, whereas Unified Extensible Firmware Interface, or UEFI, includes this functionality by design. If a drive is not detected during installation, it is important to confirm that the motherboard supports the interface and that boot settings are configured to recognize the device correctly. Installing an M.2 solid-state drive is straightforward, but it requires precision. The drive is inserted into the M.2 slot at a shallow angle and then pressed flat against the motherboard. A small screw is used to secure the drive to a mounting standoff. The system must be powered off during this procedure to avoid damage. Once installed, the system firmware should detect the new storage device. If the drive does not appear in the BIOS or UEFI, users should double-check the slot type, keying, and whether the motherboard supports the selected protocol. The use case for each type of SSD interface depends on the performance needs of the system. SATA solid-state drives are sufficient for everyday tasks such as operating system boot, web browsing, and document editing. NVMe drives are ideal for high-speed applications like gaming, multimedia production, or running virtual machines. PCIe drives with large form factors are used in enterprise environments where high throughput and reliability are essential. Selecting the right type of drive involves balancing budget, speed requirements, and system compatibility. Thermal management becomes important when using high-speed solid-state drives, especially those based on the NVMe standard. During extended read or write operations, NVMe drives can generate significant heat. If not properly cooled, the drive may throttle its performance to avoid overheating. This is why some drives include pre-installed heatsinks, and many motherboards come with thermal pads or covers. In compact systems or laptops, special care must be taken to ensure adequate airflow or passive cooling, particularly when installing multiple high-performance drives. Solid-state storage upgrade options differ between laptops and desktops. Laptops often have limited space and may support only one M.2 or 2.5-inch SATA slot. Some Ultrabooks even have soldered storage, making upgrades impossible. Desktops, by contrast, provide multiple options for SATA, M.2, and PCIe expansion cards. This flexibility allows technicians to choose faster or higher capacity drives based on available slots. When upgrading, it is important to verify the supported interface, the physical dimensions of the drive, and the firmware requirements of the system. Solid-state drives, like all hardware, can experience failures or degraded performance. Common symptoms of SSD issues include a drive suddenly disappearing from the system, slower write speeds than expected, or operating system boot failures. In some cases, these problems are caused by outdated firmware, corrupted file systems, or wear from excessive write cycles. Diagnostic tools from the drive manufacturer can provide details such as remaining lifespan, error counts, and drive temperature. Monitoring these values helps prevent unexpected data loss or downtime. To maintain the health of a solid-state drive, technicians should use monitoring and diagnostic utilities provided by manufacturers. These tools display attributes such as drive temperature, usage hours, and error rates. Most drives support SMART, or self-monitoring, analysis, and reporting technology, which logs various health indicators. Operating systems also include tools to report whether a drive is mechanical or solid-state, and whether features like the TRIM command are enabled. Regular monitoring ensures that problems are identified early and that the drive performs as expected throughout its service life. In summary, understanding solid-state drive interfaces is critical for selecting, installing, and supporting modern storage technologies. The exam requires knowledge of SATA, PCIe, M.2, mSATA, and U.2 interfaces, including their protocols, performance characteristics, and installation requirements. Each interface type has specific use cases and constraints, making it important to match the drive to the system it will be used in. Recognizing connectors, slot types, and configuration steps will help technicians make informed decisions and solve storage-related problems effectively. Thank you for listening. Please visit baremetalcyber.com for more cybersecurity information, podcasts, books, and more.